Swayam Prabha. Digital India. Educated India.
You have had about 10 lectures till now? More than that? 17 lectures. Ah, you're lucky, huh? So we never had this kind of opportunity when we were at your age. Huh? So, and also you are lucky because your friends who are left behind, they don't have this opportunity, right? So you have to go and help them. What you have learned and a little bit pass it on to your friends also in the colleges or wherever you are studying, right? So how many of you are absolutely from a rural background? Rural means absolutely rural. Don't hesitate, I am also from rural. Now I think everybody will raise hands. Huh? Right? I also came out from a absolutely rural background. Absolutely didn't even know how to speak English. Right? Only language I knew was the Telugu. Nothing else. Okay? So that should not deter you. You can pick up, you can do good things, wonderful things you can do in your life, right? Okay, while you are doing something, achieving something, you also help others around you, so that they will also do something, right? They will also be happy, right? You should be happy, you should ensure that others also, some happiness you should share with them. All right? Okay. From Chennai city, how many of you are there? Chennai city, Trichy city, or Madurai city? From city? Huh? It's not Madurai. Madurai district, right? Okay. Anybody from Tirutani, this side area, Vellur, Tirutani, this area? No one is there. Okay. Okay. All right. So, you're all chemistry students or physics? Chemistry. All chemistry students, no physics. Physics students were not selected. I'm only chemistry students. Huh? Oh, they were also selected, but they went to IGCAR. So, they are purely chemistry. First year MSc or second year MSc also? Huh? Yeah. First year completed MSc and going to second year, but no second year student is there. Oh, even there are few who you are in second year already completed. Okay, so you are also given opportunity. All right. Okay, so with that background, what I am going to talk to you, how many spectroscopy techniques have been taught to you till now here? NMR, fluorescence, Professor Mishra must have taught that. Prasad, Yadaman Prasad. Who taught you fluorescence? Yeah, Javelin's diagram. Who taught you that? Yadaman Prasad. Okay. And then what other spectroscopy? What other spectroscopy techniques you have taught? A.K. Mishra must have taught. Only two? Fluorescence and NMR. Only two? Okay, good. So, today I am going to give you a heavy dose of photoemission spectroscopy. Okay? All right, 2 hours, they have given me 2 hours, so I think I will speak about that. Okay, so that is the topic of this. Little bit of fundamentals. I will not go into the too many details, but I will give you the basics of that, and then you can appreciate how to use this photoemission spectroscopy to analyze chemical compounds, and some spectral interpretation, photoemission spectral interpretation also we will talk about. Okay. To know photoemission is to know electronic structure of atoms, molecules and materials. Photoemission, for example, you talk about orbitals are there. Have you seen the orbital? We have not seen, right? And we say this electron is sitting in this particular orbital. For example, 1s electron sitting in a hydrogen atom has energy. What is the energy? 13.6 electron volts. So you make a calculation and say this is the 13.6 electron volts should be the energy of the electron which is sitting in 1s orbital, right? Bohr atom gives you all, Bohr model gives you all that. So can we measure that? How do we know whether that can be measured? What is the experimental technique involved to measure the energies of electrons sitting in orbitals? And what is the evidence that such orbitals are existing? Is there any, whatever we do, we should have some experimental method to measure, right? We always say something and then we do experiment in the lab and try to find out whether what we have said is can be measured or can be understood you doing some spectroscopy technique, right? So all these orbitals that you are talking about, atomic orbitals or molecular orbitals, or if it is material, the density of states, all of them can be mapped using photoemission spectroscopy. All right. So you can analyze atoms, molecules and materials. Materials means it can be any solid, condensed matter. Can be insulator, it can be semiconductor, or it can be superconductor. Any material you can analyze it using the photoemission spectroscopy. Okay. For example, look at aluminum. Take aluminum. Aluminum can exist as a metal. It can also exist as aluminum oxide. What is the difference between these two? Oxidation states are different. Pure aluminum metal has oxidation state 0. Aluminum oxide has oxidation state +3. How do you know that? Have you gone and seen that? Right. So we should be able to find out a measure. Should be able to make some measurements to say that it is aluminum is in 0 state and aluminum is +3 state in oxide, etc. Right. Photoemission is a very good technique to look into these things. Okay. Now you look at this aluminum powder. If you mix it with ammonium perchlorate, and it gives you rocket propellant. The rocket fires, initially you have this aluminum powder also they use there, right? But then they don't use aluminum oxide powder. They don't use aluminum oxide powder. It is inert. It is inert, right? Same aluminum, but the oxidation state is different, right? And then one is active, other one is not active. So people start looking at what is making this active, other one is not active. What is the oxidation state? What is the chemical environment present in the material, etc. Okay. So to analyze that, for example, even aluminum foil, if you take in our houses, it's also inert. That is also inert. It doesn't really react. The reason is that aluminum foil has a thin layer of aluminum oxide, very thin layer of aluminum oxide. So we should be able to analyze that. So that is where the photoemission spectroscopy comes into picture, because photoemission spectroscopy is surface sensitive. Surface sensitive. It doesn't look into the bulk. For example, X-ray diffraction, if you take X-ray diffraction, it gives you bulk information. You know what is X-ray diffraction, right? Some of you. X-ray diffraction, Bragg's law. So there you get bulk information. What is the structure of this material? What are the unit cells? What are the reflections that you have? You analyze that and then try to get the structural information. Okay. Look at this particular slide where you have variety of. I have just taken some of them. Beryl, the green compound. White, this calcium, chromium silicate, titanium oxide, aluminum, anatase titanium, rutile titanium. All these are all materials. Now in this, you have all these elements. Beryllium is there, aluminum, silicon, oxygen, calcium, chromium, titanium, and all that. Right. It's a solid. So I should be able to take a solid and record a spectrum and then say that in this solid has these elements. And also not only these elements, this element is present in this particular oxidation state, right. So that is possible if you do photoemission or both are same, photoemission or photoelectron spectroscopy analysis. If you do, you will be able to analyze that. Okay. Now this photoelectron spectroscopy was originally developed by Kai Segban, University of Uppsala, Sweden, and he received Nobel Prize in 1981. 1981. The photoemission experiment itself, explanation of photoemission itself was given by whom? Photoelectric effect was originally Albert Einstein. That is in 1905. But then it took so much of time, 1905 to almost 60 years to develop this photoemission into a spectroscopy technique because of various technical reasons. It took nearly 50 to 60 years to develop it into a spectroscopy technique, which we are all using today, which we are all using to analyze our samples. Now look at this. Let us say this is a metal plate. For example, you can take it as one of the either copper or potassium or cesium, some metal plate, and then you take some light. It can be X-ray or UV, right? You can take that and shine it on that. So this metal plate, metal has free electrons. Right? These free electrons move around. So these free electrons get ejected. Now they absorb light and these electrons come out. Ejection of these electrons. And these electrons, if you catch them, you can get information about chemical shape, binding energies, chemical state of the metals, the ions present here, or even atoms present in this particular metal plate. Okay. Now, a spectrum, this can give you a spectrum. What you get is a photoelectron spectrum. In this case, you vary the frequency and intensity of the electromagnetic radiation. You can vary either frequency or intensity. Frequency, if you vary, what changes? Energy. It is related to energy, right? Increase the frequency, energy. Now intensity, you can have more number of photons or less number of photons focused at a particular point. These two things can be varied. If you vary them, if you vary the intensity, for example, then you get more number of photoelectrons. So this light is more intense, you get more electrons out, right? If this light has higher frequency, then you will get energy. The electron energy will go up, right? Higher the frequency, higher the kinetic energy of the electrons which are coming out of the sample, right? So this is brief. This is nothing but, if you recall, photoelectric effect. This is nothing but photoelectric effect. Okay, so that's what is I have plotted here. For example, here this is the frequency of the light that you are using, and that the kinetic energy of electrons which are actually coming out of the sample. And then this line is touching here. That is the threshold frequency. So if you want to have electrons to come out, you should have minimum frequency. That is called threshold frequency. If you have a photon, what is photon? Photon is nothing but a packet of energy basically, right? Okay. If the photon energy is less than nu t, for example, somewhere here, then the energy is not sufficient for the electron to get ejected, right? So, as a result, you will not get any photoelectrons. You will not get any photoelectrons. Even if you use a very intense light, you will not get anything out of the sample. But then if the frequency of the photon, the light frequency is nu t or more than that, then you start seeing electrons coming out with certain amount of kinetic energy. Okay, all right. So, this frequency which you are talking about here, this frequency is nothing but threshold frequency, which is often called work function. Work function. I am referring to solid. I am referring to solid. Okay, that is nothing but work function. So, that is what is given here. H nu is equal to phi. H nu is equal to phi here. Now, H nu is equal to half mu square plus phi. If it is a solid, then the electron will come out with this much of kinetic energy. Half mu square is the kinetic energy factor, kinetic energy of the electron. So, it will come out with this much of kinetic energy, overcoming the work function. Suppose if it is not a solid, you can have a gas, a molecules or an atom, get a gas phase system. If you take, then the gas molecule has to be ionized. So, there is no work function. Work function is related to only for solids. Then you have ionization energy. So, the electron which is coming out now has to get ionized, and then it will come out with this much of the half mu square kinetic energy from the sample. Gaseous sample I am talking about. It can be gas, can be atomic, for example, you have rare earth gases, for example, or any of these simple atomic systems or molecular systems. Okay. So, overall what you have is E kinetic energy is equal to H nu minus E binding energy plus phi. This is referring to solid. Okay. So, your H nu has to be sufficient enough to overcome the work function and then overcome the binding energy for the electron to come out of the solid. Right. So, basically what you are going to get is the binding energy of the electron which is sitting in the solid. Suppose you have in the atom you have 1s, 2s, 2p, etc. electrons are there. So, 1s electron has a different binding energy, 2s has a different binding energy, right? P electron will have a different binding energy, d electron will have different binding energy. So, that means that you will be able to study, you able to determine the binding energy of the electron that is coming out of the system. In other words, the binding energy of the which is related to that particular atom, particular level in a particular atom can be determined. Okay, all right. So, here the number of emitted electrons is proportional to the light intensity. That as I mentioned to you, that more the intensity, more number of electrons will come out, and the kinetic energy of these electrons which are coming out are independent of the light intensity, whether intense light or dull light, but if the frequency matches, it will come out. Okay. So, number of electrons are emitted unless no electrons are emitted unless nu is greater than nu threshold. That is also a condition. Okay. All right. So, kinetic energy of the emitted electrons depends on the frequency. So, this is nu is important here. See, nu should be more than this. If it is less than that, kinetic energy will not have any kinetic energy. Okay, electrons will not come out of the sample. So, this is basically kind of a summary of the photoelectric effect, which we have, you are all familiar. All right. Okay. Now, let us look at some points I have just given here. As I said, photoelectric effect is first described by Einstein in 1905, and based on that the spectroscopy has been developed, right. And in IIT we have at least a couple of spectrometers are there in IIT. One is going to come to chemistry department soon. It is ordered. So, probably in another few months it will come, and then you will be able to use them. So, it is a spectroscopy is experimental technique to determine the relative energies of the electrons in atoms and molecules and solids. This is experimental technique. If somebody asks you, I have a element, I wanted to identify the element, or I have a mixture of elements present in a particular sample, mixture of atoms present in a sample is a mixture of atoms. You wanted to find out what are those atoms. This is the technique which can be used. So, you should also keep in mind here, you can analyze solids, gases and liquids also. Liquids is very difficult, it needs a special equipment, special experimental design to analyze liquids, but solids and gases can be analyzed. Gases also, all these three, for solids there is a different kind of spectrometer, for gases you have a different kind of spectrometer, for liquids you have a different kind of spectrometer. All are photoelectron only, but they have different type of spectrometers. Okay. So, the standard expression that you probably should keep in mind is binding energy is equal to h nu minus kinetic energy. That is the standard expression. The R binding energy plus kinetic energy is equal to the h nu, the photon energy that you are using. What are the photon energies that we generally use in the laboratory equipment is that magnesium K alpha radiation, which has 1253.6 electron volt, aluminum K alpha radiation, h nu is equal to 1486.6 electron volt. These energies are very precise, they are monochromatic, very precise energies. Because if we should know the h nu value precisely, then only we will be able to estimate binding energy. If h nu keeps varying, then you will not be able to get the binding energy correctly, right. So, h nu has to be precisely defined. Once you define this, like in this case for example these two, and then you can measure the kinetic energy of the electron that is coming out. So, you know this value h nu, you know this value, so you subtract that, you get the binding energy of the electron that is coming out from the sample, or from atoms present in the sample. That is more precise way of saying that. Okay, all right. So, photoelectron spectrum is now nothing but number of electrons coming out versus the binding energy or kinetic energy. It can be number of photoelectrons coming out in the y axis and then kinetic energy or binding energy. That is a photoelectron spectrum basically. That is the photoelectron spectrum. All right. So, you can have for X-ray photoelectron spectroscopy, there are two things here. Once you come to, until now we said photoelectron spectroscopy or photoemission spectroscopy, both are same essentially. There was another name called electron spectroscopy for chemical analysis. Earlier people used to use that language. Electron, that is called ESCA, electron spectroscopy for chemical analysis. All are same, but then in this case, in the photoelectron spectroscopy, if you use X-rays, soft X-rays, these are the soft X-rays. If you use that of the order of 200 to 2000 electron volts, then you basically call it as X-ray photoelectron spectroscopy. That is, this analyzes the core levels. Okay, I will explain you what this core level is. If you use ultraviolet light, for example UV radiation, which is of the order of 10 to 45 electron volts, then you analyze only valence levels. Okay. So, if you are analyzing core levels using X-ray, soft X-rays, then you call it as X-ray XPS, X-ray photoelectron spectroscopy. If you are using UV light and then analyzing the valence levels, you call it as ultraviolet photoelectron spectroscopy. Okay. So, depending on what radiation you are using to do the experiment. Okay. Right. Now, the so the photoelectric effect basically Einstein got Nobel Prize in 1921 because he explained it. All that he said was kinetic energy plus binding energy is equal to h nu. He got Nobel Prize for that. right? Now we find out that is very easy, but for him it was not easy at that time, right? So many things that you identify, you study or you come across, there is a very small thing, you should be able to grasp that. Very, very small thing, but it will have a lot of meaning in science. You should be able to catch that, right? So once in a while you should think out of box thinking is important. Out of box thinking is important to catch the concepts. Okay. So now, so this, as I said, from 1905 to all the way 1960, it took nearly 55 to 60 years. This Sigman, Kai Sigman is the person who started working in this area, developed this spectrometer XPS technique for analysis, and for that he got Nobel Prize in 1981. He had to wait another 20 years to get Nobel Prize, right? So if something has to be done, one has to invest the lifetime, right? Yeah. So that's what I said. X-ray photoelectron spectroscopy is also known as electron spectroscopy for chemical analysis. People used to call this earlier. It is almost 65 years old. 65 years is my age. 65 years old. Now let us look at this. So we have given so far, some background. This one. Now I will just showing you this particular slide. I want you to explain what this is, what this means. So magnesium, silver, lithium, potassium, all these 4 elements, they are the kinetic energy of the photoelectron and incident photon energy. What does it tell you? What is it telling you? Some conclusions based on what I have explained so far. Okay. Any other? Can you say something about, analyze this slide? Right. For example, if you take these 4, for silver, the incident photon energy is somewhere around 4 here, much higher than magnesium or lithium or potassium. It means work function is very high. Work function is very high. That's the reason why you need a higher photon energy to get electrons out. Suppose if you use any of this energy, photon energy, you will not be able to ionize any electron from silver. So that is the threshold frequency required. That is the threshold frequency required. And this frequency and beyond that, you start seeing photoelectrons coming out from silver. Whereas you don't need this much of energy for potassium or lithium. For lithium, potassium, you see it is only very small, about 2.1 or 2.3, 2.5. You need only 2.5 electron volts frequency light to get the electrons out, photoelectrons out. So the threshold frequency is very low here. That means you know that potassium and lithium is very easy to ionize. Ionization potential, do you remember? Alkali metals, alkali metals, ionization potentials are very low, which means you can use incident photon energy could be very small. It is around 2.1, 2.2 means it is UV light. That energy falls in UV light. You can calculate that and check. So if you shine UV light, you will be able to get electrons out in the from the alkali metals. So work function is very low. Work function is very low. Okay. Yeah. So that is the meaning of that. So the work function increases from here to here or from here to here. Work function of potassium is greater than work function of silver. Is that correct? No. Work function of silver is greater than magnesium, is greater than lithium, is greater than potassium. Right? Okay. Now, see, I have given you the values of some of the values of the work functions here. In this case, for example, aluminum is 4.08, and then as you keep going here, zinc is 4.3. The lowest one is cesium 2.1. The lowest one is cesium 2.1. That's what we saw. Even potassium also around 2.2. You are getting photoelectrons coming out in the previous slide, right? So cesium 2.1, that's the lowest one. So if you use the 2.1 is nothing but in the UV region, UV light. You shine UV light on a cesium metal, you start getting electrons out, which can be demonstrated in the lab also, which can be demonstrated in the lab. All that you have to have is some vacuum system where, you know, to collect the electrons you have to have a photodiode to collect the electrons and show it. Okay, all right. So these are all work functions. So as I mentioned now earlier, when you use X-rays to shine, you know, shine the X-rays on the surface of a solid or metal or a solid, it can be, then how deep they penetrate. That penetration is of the order of micrometer, Okay. Now, as they go through the sample, they start ionizing atoms there, right? These X-rays, you know, they ionize, so the electrons will start coming out. And these electrons, so that much of region, that about a micrometer region, sample gets ionized, electrons will get ionized, they get liberated. But these electrons have to come out to the surface so that they escape into the vacuum, or they escape from the sample, so that you can measure the kinetic energy of these electrons. Okay. So the signal signal is obtained only from the depth of 10 to 100 angstroms on the surface, which means that the X-ray can penetrate deep into the sample for about a micrometer, but the electrons which are coming out about 10 to 100 angstroms, those electrons will come out of the surface without losing energy. So if the electrons are coming from the deep, by the time they come, they lose some energy because of the collision. They have to pass through the sample, so they interact with the neighboring ions or even electron cloud, so they lose energy. So by then, if they come out, the energy, kinetic energy which they are coming out is not the correct kinetic energy, because they lost some energy already in the process of coming up. But the electrons which are coming from 10 to 100 angstroms, you know, those electrons will come out correctly without losing energy. So they have a memory of from which element they are actually coming out. Okay. So normally the electrons, the photons which are used in the lab is, as I mentioned to you, 1253.6 and 1486.6 electron volts. In the laboratory spectrometers, they use only these two sources, X-rays. Okay. So now let us look at this one. If this is some kind of a diagram representing atom, so these are all basically neutrons, protons are present in the nucleus, and you have electrons going around here. These are electrons. These electrons are very close to the nucleus, thus you call them core electrons. But the electrons which are far away, these are valence electrons. These are all valence electrons which are little far away from the nucleus. So which electron will have a higher binding energy? This one or this one? Core electron will have higher binding energy. So to remove these higher binding energy electrons from the core, you need X-rays. You need X-rays. If you want to remove electrons from the valence levels, these are valence levels, you need only UV light, that is sufficient. Of course, even X-rays also can remove, but UV is sufficient. Okay, all right. So that then the core electrons respond very well to the X-ray energy, these core electrons. Okay, so the X-ray comes here, it knocks out the electron, this electron will come out of this atom. This is the atomic picture, but this If it is in a solid, this electron which is coming out will have to go through the solid, right. This is a only single atom we are looking at. Now this electron, this free electron, and if you can catch it and measure what is the kinetic energy of this electron, what is the kinetic energy of this electron, you can actually measure that. You can actually measure that using analyzer. There are certain analyzers which can actually, electrostatic analyzers are there, which will help you to measure the kinetic energy of this free electron. In addition to these photoelectrons, when you ionize these atoms, in addition to photoelectrons, different kind of electrons also come out. Those electrons are called Auger electron, Auger electron, not Agar, Auger. Okay, that is some German name. Okay, Auger electrons. Okay, I will explain you little about that in the next slide. Now, this Auger electrons are also can be analyzed. That spectroscopy is called Auger spectroscopy. That spectroscopy is called Auger spectroscopy. Auger spectroscopy. How many of you have heard of this photoelectron spectroscopy before coming here? So you know it then. Yeah, XPS has been taught to you. Auger. Okay, so this is the summary of what I was talking about. The summary is that you have these levels 1s, 2s, 2p, so on and so forth. When you go up, you have a band or valence levels, right. So now you remove a core electron using a photon. This photon should be X-ray photon. So you remove the electron from here, this electron comes out, you analyze the energy of this electron which is coming out, that gives you XPS. That gives you XPS. Whereas if you see electrons which are coming out from the valence levels or a valence band, then what you get is the UPS. So these are the core levels. These are all, you can call them as core levels. Now a second process that happens here is, once you create this core hole, this electron is very unstable. This atom is a very unstable, excited atom. So then what happens is, an electron from this higher level jumps into this level here, and that much an energy difference, that energy difference is released as X-ray. And that energy sometimes can be picked up by the electron which is sitting in this level, higher level, and then it will come out. That is nothing but Auger electron, right. But the Auger intensity is very low. Very few electrons come out, Auger electrons, right. So now if you see, this is only a single step process. You just take this electron out, and then only single step process. Photoelectron, so the binding energy of this electron which is sitting in this particular level is equal to the photon energy minus the kinetic energy of the electron that is coming out, right. But then this is same principle for UPS and XPS both. Whereas in this case, now this Auger electron kinetic energy is equal to energy of this level minus energy of this level minus energy of this level. Okay. So remember, here in this particular expression there is HNU, but here there is no HNU anywhere, which means the Auger electron, the kinetic energy of the Auger electron will not depend on the initial radiation that you are using. HNU can be anything, because it is not depending on HNU. It's not depending on HNU. Okay. So this is basically a 3 electron process, 1, 2, 3 electron process, and this one is a single electron process. Okay. Okay. So, why core electrons? XPS. Now, in this case, the electrons which are close to the nucleus, or they are actually they are confined to a particular energy, right? Whereas the electrons which are actually far away from the nucleus, they move around. They move around. They are somewhat free in all directions, right? In a sense, suppose you take a metallic sample, there are core electrons which are actually very confined, because they are very close to the nucleus. They have a fixed energy. They are very localized. They are localized. Whereas the electrons which are in the valence levels, they move around. These electrons do not belong to a particular core. They don't belong to a particular core, right? As a result, you need to analyze core electrons to get information about the atom that is present in the sample. Valence electrons will not be able to give you that information. Okay. So, for that there is something called Fermi level. How many of you are familiar with Fermi level? Fermi level is basically the highest energy level that is occupied by the electrons when at zero Kelvin. At 0 Kelvin. Beyond that, you may still have energy levels, but you don't have electrons to fill up. That is the maximum that you can reach. That is called EF. EF is very important because that EF is taken as a reference point for our spectra, for photoemission spectra. Okay. So, since core electrons are local, very localized, local, close to the nucleus, they have the binding energies which are characteristic of that particular element. Characteristic of that particular element. Okay. So, if you measure the kinetic energy or binding energy of that core electron, you will be able to say what is the element that is present in the sample. What is the element that is present in the sample. Okay. Now, the core electrons have higher probability of matching with the energies of aluminum alpha, magnesium alpha. Generally, these aluminum alpha, magnesium alpha energies are sufficient to reach core level electrons, which can give us information about the element present in the sample. Okay. All right. These are the energies. You can remember these energies. Okay. How does XPS work? So, for XPS to work, you have to have a monochromatic X-ray beam. Monochromatic X-ray beam. The energy X-ray beam that you are using should have a very precise energy, very precise energy. Okay. So, that is one. X-rays either of two energies, as I mentioned to you already, and then these X-rays penetrate to up to about a micrometer, but the electrons which are coming out, the photoelectrons which are coming out from 10 to 100 angstroms are the ones which will give you the correct information about the elements present in the sample. You need, in addition to all these, you need vacuum. Why do we need vacuum? The electrons, see, when an electron comes out, you have to analyze the kinetic energy of the electron. Before that, if it hits something, some gas molecule, it is gone. So, you have to have a fairly large mean free path for the electron from where it is coming to reach the detector. By the time it reaches the detector, we actually have to measure the kinetic energy of that. When it is coming from the sample, it just goes out. So, you measure the kinetic energy, and also allows the electron to reach the detector. So, you have two things to do there. One is to, when it is traveling, you measure the kinetic energy, that is your x-axis. And then when it goes to the detector, it detects how many electrons are coming, it counts. I have number of counts, is nothing but number of electrons coming out. So, that will give you intensity. That will give you the intensity. That is nothing but your photoemission spectrum. That is nothing but your photoemission spectrum. Okay, all right. So, to do that, you need to have your UHV, ultra high vacuum. What is ultra high vacuum? What is vacuum? What is pressure? What is vacuum? What is the pressure in this room? One atmosphere. In torr, how many torr? 760 torr. In millimeters? What is the pressure in if you go to 5 kilometers up? Pressure, temperature? Go to moon? So, here in order to have the mean free path, large mean free path, we need to have vacuum, that is one. The other reason is that you need to have the sample clean. Sample has to be clean. At room temperature, sample gets contaminated very fast. Contamination means not the way what we are seeing. Atomic level contamination should not be there. Atomic level contamination. It should be as clean, atomically clean as possible. So, to maintain that, you need vacuum. You need vacuum. These are the two main reasons. These are the two main reasons. Okay. Now, of course, we have this analyzer, cylindrical mirror analyzer, etc. Spectrometer is plotted from the analyzer signal, that is your x-axis, and then binding energies can be determined from the peak positions, and elements present in the sample can be identified. Okay. So, these are some of the things which we so when you have peaks, you just see the peak, you find out the binding energy. From the binding energy, you can find out the element. Binding energies are characteristic of the element. For example, oxygen 1s, carbon 1s, nitrogen 1s. Do you think all of them have same binding energies? No. So, by looking at the measuring the binding energy, you will be able to identify what element is present. Okay. I just wanted to give you this small thing here, oxygen atom. You are using X-ray photon, and then you remove the electron from here, photo electron coming out. Once this happens, there are 3 steps involved here. Of course, you have these names I already mentioned to you. X-ray photoelectron spectroscopy, electron spectroscopy for chemical analysis, ultraviolet photoelectron spectroscopy, photoemission spectroscopy. You should understand the terminology, what it means. Okay. Essentially same. Here you are using X-rays, here also X-rays can be used. This is ultraviolet means your energy is different, photons are UV photons. Photoemission spectroscopy can be XPS, can be UPS also. Can be XPS, can be UPS in general, right. But there are 3 steps involved in this. Absorption, ionization, initial state effect, response of the atom, and creation of photoelectron, that is the final state, and then transportation of electron from the place where it is ionized to the surface, and then escape. We are now talking about the photoemission spectroscopy of solids. Okay. Photoemission spectroscopy of gases are different, that is different, that we will come to that little later. Okay, all right. So, these are all things, 3 important steps. When the electron is transported from the ionized, from the place where it is getting ionized to the surface, it can come out from the top layers about 100 angstroms without losing energy. But if it is coming from the deep, it tends to lose some energy. So, that will constitute the background in the photoemission spectrum. Okay, let us look at the energy levels once again. Let us look at the energy levels. Now here, this is the kind of electronic structure you have. You have electrons, so you fill up all these electrons, these are the core levels. These are all core levels, very localized. And then as you go up here, these are binding, and these are the slowly you are going towards valence levels, and then you reach the Fermi level here. So up to here, all these levels are full with electrons. Okay, and then the highest level is Fermi level. So up to here you have filled the electrons, and if these are sitting in the core level, they have a very specific binding energy. But then as you keep going here, this becomes like a band, these are local, delocalized kind of, so they, this from valence levels. This region is valence level region. So the Fermi level corresponds to zero binding energy. So that means you call this as a zero binding energy highest, and then from there you measure the binding energy below. What happens to binding energy from here to here? Increases or decreases? Fermi level, as you are actually going towards the core here, it increases, right? So this you take it as a zero Fermi level, and then you keep on going down, then you start seeing binding energy increases. So your spectrum should look like that. Your spectrum should look like that. Okay? Okay. Some quick few points which I want you to answer again here. Number one, the photon absorption is very fast process, about 10 to the minus 16 seconds, it absorbs. Right? Now, no photo emission for HNU less than work function. Is that a correct statement? No photo emission for HNU less than work function phi. Correct or not? Everybody agrees? She doesn't agree. Huh? You only, you agree? It's a correct statement, or all of you agree, right? The second one, no photo emission from levels with the binding energy plus work function is greater than HNU. Is that correct? Say something. The same statement is written in a different way, right? So you should, that's what I am saying, you should think, right? And second thing is the kinetic energy of photoelectron increases as binding energy decreases. That's correct, that is right. Intensity of photo emission is proportional to intensity of photons. Intensity of the photo emission is proportional to intensity of photons. Somebody has some doubts. Those who are sitting in the back benches, back seats. Is that correct? Right? Yeah. It requires monochromatic incident photon beam. A range of kinetic energies can be produced if valence band is broad. A range of kinetic energies can be produced if valence band is broad. The core levels are very localized. Energy is very precise, but valence levels in a solid they become broad. It's a band. It's a band. Yeah. So you get variety of kinetic energies. A range of kinetic energies can be produced. Each element has unique set of core levels. Therefore, kinetic energies or binding energies can be used to fingerprint the element. That is the final conclusion. All right? Okay, good. Now let us see here. Binding energy represents the strength of interaction between the electron with the quantum numbers n, l, m and s and nuclear charge. Is that correct? Now, in gases, binding energy is equal to ionization potential. Agreed? Because in gases, all that you are removing, remove electron is the ionization potential. There is no work function there. Sorry?
Binding energy is related with solid and ionization energy is related with gas.
Exactly. Correct. Okay. All right. Now, binding energy of 1s electron is greater than binding energy of 2s electron, binding energy of 2p electron greater than binding energy of 3s electron and so on. Is that statement correct? Now, binding energy of sodium 1s is less than binding energy of magnesium 1s is less than binding energy of aluminum 1s and so on. If it is correct, why is it correct, you should tell. Why is this one correct? You said this is correct, right? Why is this correct? For correct, one mark, but why is it correct? You get 3 marks. 3 plus 1, 4 marks. Reasoning, you will get more marks. This is very close to the nuclei. So, the influence is, nuclear influence is very high. So, binding energy will be high. Whereas in this particular case, and it is all are less than. Is the statement correct? If it is correct, what is the reason? Anyone else? Any other argument? There is one argument. See, all are 1s electrons only, but then they all belong to different elements. So, sodium, magnesium, aluminum, what happens to the nuclear charge? Increases. Obviously, the binding energy is more here compared to this and compared to that. Right? You have to see the atomic number of that. So, higher the atomic number, higher the nuclear charge and higher the binding energy. For the same level, 1s, we are looking at 1s here. Okay? The binding energy of orbital is not affected by isotopes. Suppose I have a carbon 12 and carbon 13. Because you all only what you have is one neutron extra. So, that should not affect the binding energy. So isotopes may not affect the binding energy of the orbital, of any orbital that you are talking about. Okay? All right. These are some of the summary things which I have given. All right. See, it is already 3 o'clock. How many of you know interpretation? Interpretation of photoemission spectra. Have you seen photoemission spectra? Have you interpreted it? No? Okay. So, okay, before we start looking at the interpretation, I will quickly look at, tell you, XPS can also be carried out using high energy synchrotron radiation. Synchrotron facility. Synchrotron. What is that called? Synchrotron. I just want you to spend a few minutes on this. Radiation from synchrotron source. Synchrotron is basically kind of it will have a ring. This ring will have a tube, forms a ring. Inside the tube, they inject electrons, current, and they allow this current to move around inside the tube. The tube is evacuated, it just moves around. Right? So, when the charged particle is moving in a linear way, it will not lose any energy. But if you try to bend it, electromagnetic radiation, it gives out radiation. Okay? So, that is physics basically. So, what you have is that this electron motion is there in this ring, and this keeps on accelerating, and at some point when you try to bend it, it gives you radiation. This is called synchrotron radiation. This radiation is very intense compared to normal laboratory sources. This is intensity of this radiation is very high. So as a result, you get very intense X-ray photoemission spectra. X-ray photoemission spectra, that is one advantage. Second advantage is you can have energy, you can choose any value, you don't have to stick to only these values. You can take, if you want to have 1000 electron volts, you can have 500 electron volts light you can take from that, and then do your experiment. In the laboratory you have this, this is limitation, but there, since it has energy, almost from IR to X-ray, entire radiation will come out of the in the synchrotron radiation. You can choose a particular photon energy, photon of particular energy, and do your experiment, and it is very intense. So as a result, you get very good spectral intensity. Now this is actually, we have this synchrotron radiation center, Raja Ramanna Center for Advanced Technology, Indore. This is the website. I want all of you to go look into that website. Okay. Raja Ramanna Center for Advanced Technology, it is located in Indore. Government of India has spent a lot of money to build this center, and it is available. If you want to do any experiments, you can write to them. There is in the website, you can book a slot and go take your sample and go there, and they will help you. They give you accommodation. Sometimes for students they even give travel also, if I am right. Okay, so there you can do this kind of experiment. There is one XPS station is there. There is one XPS station is there. Okay, now, so this is how it looks like. The synchrotron radiation looks like this. You will have a LINIAC kind of a thing where you inject the electrons into this booster synchrotron, and then you accelerate the electrons and then put them into the larger, bigger ring. This one, this ring, main synchrotron ring. This ring diameter can be in kilometers. This ring diameter can be in meters to kilometers. Okay. And then wherever there is this is a bending magnet. This is a bending magnet. When the electron beam comes, the current comes here. You bend it, then you get a radiation from here. See, this is a radiation comes out. Radiation comes out, radiation comes out, radiation comes out, radiation comes out. Then you have an experimental station. You can build your experimental station, XPS station or XRD, single crystal XRD, even IR also can be, stations also can be built there. So for one ring, you can have so many work stations, you can have so many experiments simultaneously, people can do it. Okay, so that is the center. That is the website for that. You can have a look at it. Okay, this is called Indus 1, Indus 2 synchronous radiation sources. Indus 2, there is an Indus 1, but the latest one is Indus 2, which has 2.5 GeV ring, 2.5 GeV ring. Okay, but in the world, people have gone up to 8 GeV. 8 GeV ring. They will give very intense synchrotron light. Okay. All right. So this is the instrumentation part. Quickly, you require electron energy analyzer. See, this is the X-ray source. That is the HNU which is coming. This is a sample, and here what happens? This is a small sample, and then radiation is exposed here. This sample is exposed to the radiation. Electrons come out. These photoelectrons are taken to the analyzer. There will be this electron energy analyzer, and you will have a detector somewhere. It's not shown here. There will be a detector here to detect the number of electrons coming out. What does this do is it only measures the kinetic energy, and then once they pass through this, they should come out here. It is not shown here, and they will the number of electrons coming out is counted somewhere here. Okay, so you need X-ray source, argon ion gun to clean the surface, some neutralizer, vacuum system, electronic controls, computer, all those things. Ultra high vacuum system is required, it is minus 9 torr. Normally 10 to the power minus 9 torr is sufficient, but people go even up to 10 to the power minus 12 torr these days, very, very high vacuum, so that they can do the experiment for long time without sample getting contaminated. Okay. So your sample size is 1 centimeter square, that's the old story. Now very small samples also can be analyzed. X-ray sources are these are laboratory one I am talking about, and so on and so forth. So this is how the analyzer works. The one which I have shown you, this one works like this. See, if you have a sample here, electrons come out, these electrons are focused here, and then they pass through this analyzer. They take this path, and so to take this path we have to have a positive voltage and negative voltage here, so that they take the path. And once you know what is the voltage you are applying, that gives you the kinetic energy, okay. And then how many are coming out will be counted here by the detector, channel detector, and so this will give you the intensity of the spectrum, and then this will give you the kinetic energy of the spectrum, okay. So this is how it looks like. You have X-ray, and then you have a sample holder, specimen here. This is the analyzer, and the entire thing is in the UHV chamber to maintain the vacuum, and then the vacuum is created using vacuum pumps, turbomolecular pumps, etc. Okay, you don't have to worry about it, but when you come to IIT Madras, you will see all of them. There is a machine available now. If you want, you can go and see it. So this is a machine which was in 1980s. This machine, a very old machine, 1980s, 1970s, 1980s. This was the machine which was used at that time. This is a modern machine. This installed in ARCI next year in 2022. This thermoscientific machine. This is another machine just installed just last month in IIT Madras in the new academic complex. Maybe some of you can go and see that. Okay, and this is a machine which is built in the National Chemical Laboratory for doing specific experiments. And this one is, if you want to read, you can read it. This is published in Journal of Physical Chemistry to 2013, volume 117, page 4717. Okay. And also you can see accounts of chemical research. Some of you are interested to know more about this. There is a nice article, Accounts of Chemical Research 2025, just this year, volume 58, page 11 to 23. This talks about this kind of machines. People make custom made machines to do some research. What I have shown you earlier was basically the commercial machines, but these are the ones which actually use the specifically made for doing experiments. Okay, all right. Okay, all right. So let's come back to this. So we'll take a break a little bit quickly.
SwayamPrabha, Digital India, Educated India.